I'm man enough to admit it, I made a mistake. And thankfully, Jeran called me out on it. In my video from several months ago where I discussed Jeran and his belief that planes could travel faster than we believe they do, I was relying upon the premise that on the AE map, or on any other flat Earth map, the southern hemisphere has to be exponentially larger than it actually is. And in doing that, I decided to do the numbers, how fast the planes Jeran was talking about would actually have to be going, and to see if the information he was providing would conform with these distances. Well, I was wrong, and I used some information that was incorrect. And Jeran called me out on it when I was doing my presentation over on Ranty's channel. And I want to thank you right now, Jeran. Because of what you identified, I'm now able to actually run the numbers correctly. And I will be doing that here in a minute. But first, I want to show you the mistake that I made. The premise of the idea is that on a flat map, everything in the southern hemisphere gets exponentially larger rather than the lines of longitude reconverging back down again at the South Pole. And by measuring distances from the North Pole to locations on the southern hemisphere map, you're able to identify what the AE distance would be. And in the process of this, I measured the distance that Jeran had identified as a plane being off of GPS tracking, so that during that time, he believes the plane would be going faster than it actually claims to be. When doing my math, I measured from the North Pole to just off of New Zealand and just off of Chile. Using those distances, and then the angular separation based upon the longitude, I calculated on the AE map how far those 2 points would actually be apart. On the globe, we're talking just over 8,000 kilometers. When I originally ran the numbers for Jeran, I came up with 18,000 kilometers, which in and of itself is a big issue for him and his fast-flying planes. But he pointed out that it appeared that I was using the wrong place off the coast of Chile, because I had the distance from the North Pole to New Zealand as just under 15,000 kilometers, but I had the location for just off of Chile at just under 9,000 kilometers. And he didn't think that sounded right. Well, you are absolutely correct. That is not right. I spent about a half hour trying to figure out where I went wrong, because I wanted to make sure that I was right first. And once I identified that I was not right, I couldn't figure out how I came up with this number. Because I used this website right here that allows you to plot two specific locations on a map, and it will tell you how far apart they are. I ran the numbers, and I ran the numbers, and I ran the numbers, and it kept coming back to the same results. But I knew it was wrong. So I even put out a call to the community to try and figure out where I was going wrong on this. Thankfully, Jay Brown responded and started working over this information with me. And then he asked me a question that made me realize where my mistake was. Do you see it? Do you see where I screwed up? I wasn't measuring the distance between the North Pole and New Zealand and Chile, because the North Pole is 90 north and 0. I was measuring from 0 and 0, which is actually on the equator at the prime meridian. Clearly, this information is not correct. I really want to thank Jay for helping me identify this information and helping me run the numbers multiple times after we got the math right, just to make sure I hadn't made a mistake somewhere else. Please go take a look down in the description. Links for Jay's content are down there. Go check him out. He's got some pretty interesting stuff. And he's also a great guy. So now I present a correction to my original video. The information that I had wrong the first time has now been updated to reflect the actual distances that Jeran's plane would have had to have flown on the southern hemisphere. Again, Jeran, thank you for calling me out on this error. If I'm wrong, I'll admit it. Enjoy. Welcome back to the Pancake World, everyone. This week, we are going to again examine the southern hemisphere on this pancake of a world. And today, we're looking at a claim made by Jeran. Jeran has long proclaimed that we don't know how fast planes actually go, because on a flat map, as I showed you last week, the southern hemisphere is not the size that we all believe it is. If you haven't watched my video from last week, here's a link to it. I highly suggest that you watch that video first so you can fully grasp the distances we are talking about today. Our old friend Jeran has found an article that he believes proves his feelings of the southern hemisphere and how planes can actually get from Australia to South America. So let's see what Jaron has to say.
What's going on, everyone? It's Jaron from Jeranism, back with a short video for you. A video where I will be showing you a recent article that allows me to feel, in a way, kind of vindicated. A while ago, when talking about planes traveling in the southern hemisphere, I stated that those passenger planes could be traveling faster than the speed of sound and actually be traveling much greater distances without anyone knowing.
Well, this should be interesting, because as I showed you last week, the southern hemisphere is enormous compared to how the globe would portray it. So how do planes actually get across this giant, vast distance of the southern hemisphere on a flat Earth? Surely Jeran has evidence to back up his new beliefs.
The jet stream is moving so fast right now that commercial planes are traveling faster than the speed of sound. If you're flying east today, you're in a whole lot of luck. The jet stream, that funny little channel of high-altitude air that flows over the United States and northern Atlantic, is moving at unheard-of speeds, delivering commercial jets to their destinations nearly an hour ahead of schedule, the Washington Post reports. In fact, one Virgin Atlantic flight traveling from Los Angeles to London notched a speed of 801 miles per hour over Pennsylvania, which, had it been on the ground, would have been faster than the speed of sound.
Well, maybe he's got something here, because if planes can actually travel that fast, maybe they could traverse the distances of the southern hemisphere required on a flat Earth. What else is there, Jaron?
All right, here you see I've brought up Flight Radar 24, which is a site where you can track flights, and I've just typed in Sydney to Santiago. And if we zoom in here, you can see what happens. And the problem that we have with these flights is that as soon as they take off from Sydney, it gets out over the open water and, of course, drops off and just skips to that next location. And then it will fly over New Zealand there. And again, once it gets to a certain spot, it just disappears from radar until it appears all the way on the other side over here by Santiago, Chile. So again, you can see that this plane got up to almost 680, I think I saw 684 miles per hour ground speed, and then it disappears. So we have no idea how fast this plane could be possibly traveling once it gets up high enough to be in those jet streams and traveling across the Southern Ocean. And then you don't see it till it hits the other side. So we have no idea what's happening in this downtime where the satellites can't pick up, I guess, the speeds of this plane.
Damn it! He's got a point. I'm sure he's done the math, and his math is right.
And so this is just a little quick example that I made here. Let's say we've got a plane going Sydney to Santiago, as we just showed. That travels 7,000 miles in 12 hours, which is about the average flight time. 7,000 divided by 12 equals 583 miles per hour. All right, but what about the jet stream? So remember, it's helping the plane with close to 250 mile per hour winds. So if the plane is being helped, well, 583 miles per hour minus 250, is the plane actually going 333 miles per hour? And then it's getting the extra 250 to end up at 583? Well, that doesn't sound very efficient, does it? So let's look at it this way. What if that plane was actually going 625 miles per hour, which we saw, ground speed. We also know that that's easily under the speed of sound. 625 miles per hour plus 250 miles per hour, which would be the most efficient thing, is 875 miles per hour ground speed. Okay, so a plane from Sydney to Santiago could be going 875 miles per hour for 12 hours. 875 times 12 is 10,500 miles instead of 7,000 miles. I mean, quite a difference, right?
So Jeran is questioning the distance and speed of the airplanes as located off of New Zealand and off of the coast of Chile. So let's take that information and see what does it tell us with basic geometry. So here's our location off of New Zealand. A little bit off of the coast, kind of like Jeran showed. This is about the point where it dropped off of the GPS. And then we've also got our location off of Chile. Now, to figure out this in geometry, we need the distance between the North Pole and that spot off the coast of New Zealand. And when we measure that, we find that it is 15,174 kilometers from the North Pole. So that is our measurement number 1. Now we have our location off of Chile, and you'll notice that it is a significant distance farther north on the map. We'll just say that rather than a globe. And the distance between that location and the North Pole is 13,866 kilometers. So we now have our distance 2 for our triangle. Now, on a globe, the distance between these 2 points is 8,280 kilometers. Now, I know Jeran used miles, but I'm trying to stay international here, so we're going to have to do a little conversion. This unaccounted for time, when the satellites don't see this plane, is just over 8,000 kilometers. So the next question we have to ask is, how far apart are these locations? Because on the globe, like I said, that's just over 8,000 kilometers. But if you use flat Earth math, first we need to know how far apart they are in degrees. And based upon basic map making, these two locations are 102 degrees apart. Now when we create our triangle with sides of 15,174 kilometers by 13,866 kilometers, with an inner angle of 102.7 degrees, the distance between these 2 points is not 8,280 kilometers. It's 22,561 kilometers. That's 16,000 kilometers, more than Jeran was expecting. So how fast would a plane have to be traveling to traverse that distance in that time? Well, I'll be honest right now and let you know that when I did this math initially, I didn't think it was that big of a difference. Because when you traverse that distance in 12 hours, you only get a speed several hundred kilometers an hour faster than Jeran is claiming, which is still more than any jet plane has ever claimed to travel. But what I'd forgotten is that it's a 12-hour flight from airport to airport. But we're not measuring airport to airport. We're measuring unaccounted for space over the ocean. And that time was only 8.5 hours. So in that 8.5 hours, this plane had to traverse 22,561 kilometers. And when I use Jeran's math, 22,561 divided by 8.5, how fast does our plane have to be traveling? It's not the 1,289 kilometers an hour converted that Jeran claims. It's 2,654 kilometers per hour. So Jeran, unless you can find a jet stream that has a speed of 1,600 kilometers an hour more than you're thinking it does, your math doesn't add up, and the planes can't fly that fast over the distances it has to be on the flat Earth southern hemisphere.
Interesting. Interesting there. That's interesting.